Good afternoon, everyone. Thanks all for coming. I am Harshal Patil, and I will be talking about enhancing the device support in Kubernetes using something called CDI and how it interacts with CRI-O, CRI runtime. So roughly the agenda, we would go over what is CRI-O, overview of CRI-O, overview of CDI fundamentals, like what's a CDI, how it is defined, how CDI is integrated in CRI-O, and some practical applications and use cases of integration of CDI with the CRI-O. We can have some time for Q&A also at the end. So why CRI-O? It's a CRI-O, if you see, it's a CRI runtime, but what sets CRI-O apart is that it is completely oriented towards Kubernetes. In a sense, it does everything in its existence. It does it for being with Kubernetes. So including the release cycles, the feature development, there is nothing else for CRI-O to do apart from just being inside a Kubernetes cluster. So that kind of keeps it, helps us essentially do optimizations. For example, when a generic plague tries to list pods in kubelet, CRI-O has an optimization to return faster without hitting the without traversing the cgroup FS using cache. We also have experimental features in developing in CRI-O. We use annotations for that, and CRI-O is also designed from the security point of view, where because it only targets Kubernetes, the attack surface is very limited. There's nothing else there is nothing else. We no other way to use CRI-O other than using it via Kubernetes. Right? Maybe so that is where we believe that minimizing this attack surface helps make CRI-O a more secure CRI runtime. We are also very quick to adapt to new security norms. For example, we have something called SecCom artifact support. So essentially, you can have your SecCom configuration nicely kept somewhere in registry, and we'll pull it up and apply the SecCom profile. Moving on, this is generally how a CRI runtime will look like. So gRPC is a CRI interface, and where you have image service, you have runtime service, and there's different components that CRI-O interacts with in order to run the containers. Going forward. And these are some of the our adapters which essentially help us stay motivated to make CRI-O better and better with every release. Now going to the CDI aspect of it. So what is a CDI? It's essentially if you expand it, it translates to a container device interface, and it's a specification for CRI runtimes such as CRI-O. To support third-party devices. It is greatly inspired from how the container networking interface is designed, and we'll dive deeper into that. But before that, who should generally know about CDI? So, for example, if you are a manufacturer of an accelerator, like say GPU, or if you have custom hardware like FPGAs, or for that matter, any device that you want to be used inside a container in Kubernetes, and which requires complex setup. For example, you might need mounting a file system from host. Maybe it has drivers that are required for your device to work. Maybe you need to perform some OCI hooks to prepare the device, maybe initialize the device. You might need more than one device node. Simple having /dev my device is not enough. Maybe you need /dev /my device 1, 2, 3, and that is what makes your device work inside a container. You might want to have specialized runtime, specialized environmental variables. I gave the example here of what NVIDIA does. Essentially, they set this NVIDIA visible devices, and you can set the UID of the GPU or the mix slice, and you can access that device. So apart from the device manufacturer, people who are developers of, say, classical device plugin and the upcoming DRA driver would also help it also help them to know what the CDI device is, because they are the consumers of this CDI spec file. So this is how a roughly sample spec file looks like. So is the cursor work? Yeah. So this is how you identify device on the host, right? You say vendor.com/device and equal to my device is my first device here. And this container edits is essentially a way to tell CRI-O or CRI runtime that, if this device has to be used in the container, inside the container, please set this environment variable. These device nodes should be made available. I want these mount paths from the host to inside the container to be ready. And some of the hooks, like I just gave for brevity, I just mentioned the one hook here, but there are other 5 hooks like create container, start container, etc. That you can use to inside this container edit. Now, if you notice, there is another container edits at the bottom here. So a lot of times your devices, let's say you have GPUs, like say you have 4 or 5 GPUs, and they all need to be set up in a similar way. So you don't want to repeat these edits every time. So if you my device 1, 2, 3, and every time you just keep repeating the same struct, right? Instead of that, what you do here is you define them in the container edits, and this will be more clear. I have an example of it, how NVIDIA does it in their CDI spec. But the gist of it is that all the configuration that is required to configure your device types, they go in this container edits, and the configuration that is required for this specific device in this device type go here, right? This is just this neatly avoids a duplication. So how does CDI work in CRI-O? So CDI, usually you have a CDI spec placed inside a specific directory that CRI-O monitors. By default, CRI-O monitors etc CDI, etc var and CDI. Who places this CDI spec inside? It could be a device driver. It could be a daemon set that just say can list the devices and generate this CDI spec. So CRI-O essentially is monitoring these devices. What happens after that is fully qualified name, like I just mentioned, device.com, my devices, device.com/devices equal to my device, is passed to CRI-O via kubelet using a CRI flag called CDI config, and then CRI-O locates this. When the CRI-O gets the CDI device, CRI-O essentially goes into these directories like etc CDI, var and CDI, and it reads all the files and tries to find the device using its fully qualified name. And then what happens once it reads it, you saw in earlier the container edits right here. It will start applying these artifacts here on the OCI runtime spec. So your container will essentially get modified. Let me go over this diagram here. So when you're dealing with, say, a classical device plugin, right? You need to implement an allocate method on device plugin. So what you do is, in that allocate method, you will essentially decide which device. For example, if the user asks you in a power resources, saying, I want resources limits and NVIDIA GPU and resource quantity 1. Now, as a device plugin, what you need to do is you need to go ahead and read this device spec that is generated, a CDI spec that is generated, and you're going to select, say, a GPU 1 here from the list of available device specs in the CDI spec. Then this device plugin will essentially return these CDI names, 1 or more, depends on the request, to kubelet. Kubelet will forward these CDI device names to CRI-O via CRI, and then CRI-O will, as I said, it locates those CDI files, CDI spec files, and it will read them, and whatever the constituents container edits that we saw, it will apply them on OCI spec. That will be passed to a runtime like crun or runc, which actually runs the container. And just for a brevity, I gave example of create container is OCI hook I specified. If I would have specified OCI hook, it will get executed at this point. But there are other hooks that also you can use here. Like this is example I gave. So, and how does it look with the new DRA driver? So if you see in old style DRA plugin, classical DRA plugin, you have resources limit, this way of specifying the resources that container needs. And in DRA, you're going to switch to using resource claim. So you're going to say resource claim GPU, single GPU, and again, the same thing, it has to be translated to a fully qualified name that CRI-O can use in your device spec. So again, the kubelet will, when the pod is getting created, kubelet is going to call node prepare resources on your DRA plugin. DRA plugin is going to return the CDI names, CDI device names, and the flow is essentially identical after that, where CDI device name is forwarded to CRI-O, CRI-O modifies the OCI spec, and you can the runtime, which actually is responsible for running the container, will essentially run the container using the modified config.json, that is your OCI spec. So integration with CDI of CRI-O, how does it look like? So CRI-O essentially, as I mentioned, it leverages CDI specification to read device configuration. Like, what do I need to set this device up? Do I need to mount a file? Do I need to run an OCI hook, etc.? Default spec directories in CDI are, these are default CDI spec directories in CRI-O are CDI, etc CDI, and var run CDI, but this is configurable. You can edit the CRI-O config to change these defaults. It greatly simplifies device management, because imagine if you are using a rather complex device without CDI, there's no standardization of what operations I need to perform so that this device is accessible and usable inside the container. What CDI does is it abstracts that out from a Kubernetes user, if you will, and places the burden of creating right CDI device on the manufacturer. Right now, if you can create the CDI spec, by the way, but a manufacturer can always come up with the better CDI spec because they know what it takes to run the device. And then from your point of view, you're just using a CDI spec, whether it's an AMD GPU or it's an NVIDIA GPU, it doesn't matter. You're just referring to a standard CDI spec. So, and then from the CRI-O point of view, there is no restart required. You can add, remove device specs on the fly, and CRI-O will just detect that, oh, this device is no longer available to me. Practical use cases of CDI that you see, as I mentioned, GPU acceleration. You can use GPU acceleration using CDI specs. Custom hardware supports, like, if you have specialized network cards that need to be initialized in specific way inside the container before need to be used, you can use CDI. FPGAs is a good example. Complex devices, you can construct a flow where you can say, I want a GPU, but I want with specific network. So what you can do is your device driver or device plugin or your DRA driver can actually select the two CDI spec files and return them to kubelet, and kubelet will pass it along all the way to make sure that, so you can have this setup of complicated device configurations. Sometimes you also can use dummy devices. We see this often. Sometimes people use this where a CDI spec gets created, but there's no really backing device per se. It's been used to hold as an anchor to, for example, you can have some UUID associated with the container pod, and then you can just hold it there as long as a container is running for your internal tracking purposes, if you will. I have some real-world example here. So NVIDIA has a DRA driver and how they do it. Let me just run the demo here. So, okay, so I'm on the host. I'm going into this directory where the CDI specs are there. So this is the spec created. When you install a DRA driver, this is a spec file gets created based on what GPUs are there on the system. And I happen to have 4 A100 NVIDIA GPUs. So this will be created by the device driver. And if you remember, I said, you have container edits. So it has device node, environment variables. These are the hooks you need to execute. And in the hooks now, it happens that this particular device requires create container. There are specific mounts that need to be added in the container. And this is the second container edit per device, where these device nodes also need to be added in the container or config. So this is how the fully qualified name looks like. At the bottom, kind. Kind and the name. So it will be k8s.gpu.nvidia.com device equal to GPU3. So then we go to other terminal, and we will run a sample workload which uses the resource claim from the DRA. So we go and execute a sample execute command just to make sure that we are running on real GPU. It will just print out the GPU that you have on that system. Then it will have resource claim. Then the resource claim is referred here in the resource claim template. This is a sample resource claim template, and we're going to go ahead and run this here. Okay, at least we'll say pod got created, and then let's say they are running. We go to another terminal I have open on the same machine, and here we see. Remember, we had just one CDI spec. Now we use two resource claim, so the DRA driver has gone ahead and created these two additional CDI specs in the same directory. And if you see, I was talking about there's no real device backing it up here, but they're used to track the claim of the DRA. So yeah, we see it here, and then now we go just to see the logs, just to make sure, we requested GPU using DRA, which internally used CDI, and we really got it. So that command here up, you see it returns the name of the GPU. We'll go ahead and delete it right now. And what we expect to see is, since once you delete the pod, the DRA will remove the corresponding resource claim. So we expect that the corresponding CDI device also to be removed, and it is removed. So this is how you would do it. This is just an example, but if you want to have something similar done similar, so what you'll do now, you're going to have a daemon set, say, and you're going to implement a device DRA plugin interface, and as I mentioned here, you will have to implement this node prepared resources, which will essentially select the DRA, select the device that you want to use with this particular claim, and you will just run with the flow. With that, then if you want more resources, if you want to understand more about CRI-O, you can go to this GitHub repository, CRI-O. We also happen to have CRI-O as a default in OpenShift. About CDI, there's a very good talk by Christopher and David on GPU sharing and CDI device plugins. That will help you understand even more how this CDI came to be. And if you want to understand more about the actual device CDI interface itself, they have their own GitHub page, and I will recommend that you should read the spec if you are interested in that. I think with that I am done. I think you have questions. You can use the mic here. There's a mic here.
Hey, so is there an option to specify in the specs a fraction of GPUs instead of one full GPU for a single container?
You mean to say, in case of NVIDIA, can you specify, let's say, a mixed slice instead of whole GPU? Is that what you're referring to?
Yeah.
Okay.
Because the example you showed is showing how many GPUs you want, but is there a way to use, instead of one, just a fraction?
Yeah. So what would happen in case is that you would use the NVIDIA. Say, I'll stick with NVIDIA because you have a practical example of that. So you will use a GPU operator, and you will say MIG enable on that. You might select a, say, mixed strategy to single or mixed, and it will create the slices on the host. Then your DRA driver will essentially enumerate all the slices and should create the CDI spec, corresponding CDI specs in that directory. And when the moment they are created in the directory, CRI-O will essentially will read it, and they will be available. Yeah. All right. Thanks. Do we have any other question? Please.
My question is, so if you have to add these devices in the config file, does it mean that only administrators can add devices, or can users also add devices themselves?
So I will frame it slightly differently. So CDI doesn't magically create devices for you, right? It's a way to express the device configuration in a more structured way. Right. So all the rules that already exist to use the devices, they still exist for using devices via CDI. So if administrator was responsible for provisioning devices earlier, it will be the same in case of CDI. What helps here is that you are not. So imagine if you don't have CDI. Imagine you have multiple vendors who have different requirements in terms of what needs to be done to get this device initialized. Now you have to make sure that you actually follow these steps correctly. You need to make sure that the OCI hooks get executed properly, and there is no standardization. So there's one type of hardware might require this OCI hooks, other type of hardware might require something else altogether. So what this device spec does is it standardizes those things and hides it under cover, and you are only dealing with the fully qualified domain name, fully qualified device name. Does that answer your question?
Yeah, I mean more like the etcd path that's on the host system, right? Where I mean clusters where you have administrators and other users that do not have full access, and they might not have access to the etcd path to add these configurations. Yeah, correct. So those devices need to be actual devices need to be attached to the node by the system administrator, and the device driver itself should be installed by someone with the right privileges who can essentially, because these device drivers run with higher privileges so that they can access the hardware. So that needs to be run in that with those privileges. Yeah. All right. Thanks. Yeah. Do we have any more questions? All right. Oh, you have one. Go ahead.
Okay, I have a question. So now you write the hooks in the file path, right? So why don't you use the command in directory instead of the file path being vendor hooks or something? Because it's lead to, I wonder, it might be leading to the security vulnerable one.
So I'm not sure if you execute, let's say, for example, you're talking about OCI hook, right? Why can't I just execute the OCI hook? Yeah, definitely. This is how we do it without CDI, right? This is how we do it without CDI. But then you are responsible for making sure that you are executing the right hook. This spec, when I showed you the demo, it was not written by me. It was by the NVIDIA's divided driver. So since they make the hardware, they know what drivers are there on the host and which path to use. So it's not exposing anything more than what you were doing. It's just that what you were doing manually earlier, making sure it works without any standardization, this just automates that in a way that now there is a specification that a vendor should follow, and they should make sure that it works with that specification. Yeah.
Okay. And another question, so who writes this CDI spec file and when?
So whenever you install the driver,
driver is responsible for writing the CDI spec files.
Yes, it is. You can write on your own. So as I mentioned, like say if you know, for example, that's actually a good question. So there is a. I hope. Let me just see if I have that example CDI here. Yeah. So if you see the device, this is the default CDI spec that NVIDIA generates, right? But it might happen that, let's say, you want to change this. You don't want to have this void. You want to probably put a MIG-UID there, or you want to put all, whatever other value it takes. You can do that. You just have to disable the aspect of NVIDIA device driver to not do that. If they support this configuration, you can do it. Or let's say you decide to write your own DI driver. Definitely, you can write that either way, and you don't allow that driver to write the CDI spec. You just don't install it. You install yours.
Mm-hmm. Okay, thank you.
Yeah. All right. I think that was all. Thanks, everyone, for coming. Yeah. Bye.